Today's lecture is about hypothesis testing based on the F distribution. So last time we did the ANOVA decomposition, and on the rightmost column of the ANOVA table we calculated an F statistic and we did a sum of squares decomposition. So today we're going to continue that story and look at how these so-called F statistics are used in hypothesis testing. Okay, so hypothesis testing based on the F distribution. Okay, so let's review and mention what kind of hypothesis tests we've done so far. So we've seen hypothesis testing before, and so far we have tested hypotheses involving the betas, right? So we ask questions like, is beta j equal to 0 or not? So we've seen this. So we've tested hypotheses of this form. Okay, so for example, null hypothesis says that a particular regression coefficient is 0 versus an alternative where it is significant in the sense of not being 0. Okay, and how do we do hypothesis test of this form? Well, we did it by a t test, a test based on the t distribution. Okay, so the key thing here is they involve a single parameter involving individual parameters using the t distribution. Okay, and so now that we're in the multiple linear regression case, sometimes we'll be handling many explanatory variables, and so we may be interested in asking whether a general linear combination of these parameters is 0 or not. And so we're going to look at the more general case. So now we consider more general tests. Consider hypothesis test. I'll abbreviate that as HT of the form. Okay, so here's a null hypothesis. So this is the general form. So we're going to have the matrix A times the vector of parameters B, and that will equal the 0 vector. And so here I should point out that what are these things? So A is a matrix of constraints. Okay, and I'll illustrate what that means in just a moment. And so what is this doing? Well, you're taking a matrix A times the parameter vector. We're looking at a bunch of linear combinations of the parameters. Matrix of constraints with linear combinations of the parameters. Not with specifying linear combinations of the parameters. So that's matrix A. I'll give you some examples of that. And then also let's remember that beta. So this beta is the vector of parameters. So this beta vector looks like this. Remember, you have beta 0, beta 1 up to beta p. Okay, and so this is why we call a matrix of constraints, because when you multiply the matrix A times the vector B, each row of A is going to give you a linear combination constraint equals 0. Okay, so this gives us more flexibility in specifying a much larger array of hypotheses. Okay, so let's illustrate this by returning to our coffee example. So let me rewrite the model I considered then, and let's talk about how various hypotheses of this form could be asked in relation to that model. Okay, so here's the coffee model. So we model the flavor, that's yi, in terms of two predictors. There is the acidity, okay, so let's now, so beta 0 for intercept, and beta 1, xi1. Okay, so let's remember what these things are. So this is the response variable is the flavor of the coffee. xi1 is the acidity. And then we have a categorical predictor, and this is the example I used to show how we can rewrite a categorical explanatory variable using indicators. Okay, so we wrote it using two indicators because there were three categories. So we have beta 2, xi2, and beta 3, xi3, and then plus the normal error term, epsilon I. Okay, so how do we define these indicators? So we'll follow the setup we had when we did that example. So xi2 is 1 if we use this semi-wet method and 0 otherwise. And then for xi3, it's we set that to be 1 if we use the wet method and 0 otherwise. Okay, so we have multiple linear regression models. So there is 3. So p is 3. There are 3 predictors after accounting for the indicator variables. Okay, so we're going to call, for our purpose, we're going to call this the full model. Okay, the reason we're going to call it the full model is we're now going to apply this hypothesis testing framework by setting various constraints using a matrix A. Okay, so I'm going to list out some examples of that. Okay, so we call it the full model, and we're going to contrast that with a few examples of what we call reduced models. Okay, so examples of so-called reduced models, which we'll get by setting the appropriate matrix A. Okay, so I'll give you 3. Okay, so first I'm going to write for each. I'm going to write down the hypothesis in terms of our usual notation. So I'm going to write in terms of the individual parameters. Okay, so first null hypothesis. Let's look at is where beta 1, beta 2, and beta 3 are all 0. Okay, and so the natural alternative to that is the alternative. So it's everything but this. So the complement of this. So in words, that means at least one of these 3 betas, beta 1, beta 2, beta 3, and not 0. Clear? So that's the complement of this condition. Okay, so in words, what is this hypothesis saying? Well, if all the betas are 0, then what does the model reduce to? So, okay, so let's look at that. So if the null hypothesis is true, model. So this is why we call it a reduced model, because we're imposing constraints on the betas. So the model reduces to so what's left? You plug in 0 for these, so yi is beta 0 plus epsilon I. Okay, so that means, in other words, we're saying in this case that none of these predictors are included in the model, and so what is this hypothesis testing then? In words, then it is we call this a test of overall significance. Okay, so this hypothesis tests the overall significance of the regression. Okay, and so why we call it overall test is because this asks whether any of the predictors impact the response. Okay, so whether any of the predictors impact the response. Okay, so what we're saying here is that we can write this hypothesis in terms in this form. Okay, so these sets of constraints, so beta 1 equals 0, beta 2 equals 0, and beta 3 equals 0, can be written succinctly by multiplying a matrix A on the parameter vector B. Okay, so what matrix A gives us this condition where the matrix times the parameter vector gives us the 0 vector. Okay, so let's put it over here. Okay, so what matrix A do we need? Okay, so what dimensions will this matrix be? Okay, so let's put it here. Okay, so it has to multiply with the parameter vector, and the parameter vector looks like this. So in this case, beta is a column vector with 4 parameters, beta 0 to beta 3. Okay, so we know that this is going to have 4 columns, so that we can multiply. And then the coefficients in this matrix should specify these constraints. So the first one is beta 1 equals 0. Okay, so how can we express that? Well, that means we're multiplying 0 for beta 0, beta 2, and beta 3, and then we're putting a coefficient 1 on beta 1. So in matrix form, this would be the coefficients 0, 1, 0, 0. Okay, so when we take this vector multiplied by the parameter vector, then we get, well, beta 1, okay? And then the hypothesis sets that multiplication to 0. So therefore, this row in A captures the constraint beta 1 equals 0. And so we can do the same for the other 2 constraints. So in effect, the matrix A that we need for these 3 constraints is going to have 3 rows. Okay, so each row can code for one of these constraints. Okay, so by similar logic, to get beta 2 equals 0, so I need multiply 0 beta 0 beta 0, 0 beta 1, and then 1 on beta 2, and then 0 on beta 3. Okay, so this multiplication gives us beta 2, and then this null hypothesis sets it to 0, and then finally we have beta 3 equals 0 encoded like this. Okay, so that is the matrix A, and so therefore we've now written this hypothesis test involving beta 1, beta 2, and beta 3 in this general linear form involving the parameters. Okay, so this is an example of a reduced model that we can test whether it is plausible, and we call it reduced because in this case we're simply dropping all the predictors from our regression model and asking whether that is plausible given the data. So that's this hypothesis test. Okay, so let's give two other examples to illustrate the other kinds of hypothesis tests we can do using this general structure. So of course here, since A has 3 constraints and then there's 4 parameters, so the 0 vector, of course, the size of the 0 vector depends on how many constraints. So in this case, the rank of A is 3, and so this gives us a 0 vector with 3 elements. Okay, so let's give you two other examples. Okay, so the second one is related to the first, but let's drop fewer variables from the model. So let's set as our second example, consider this null hypothesis: beta 2 equals beta 3 equals 0. Okay, so what is this one asking? So this, so if null is true, the reduced model we get now, it looks like this. So yi equals, so we're dropping beta 2 and beta 3 from the model, so the model reduces to beta 0 plus beta 1 xi1 plus epsilon. Okay, so this is now the reduced model specified by this null hypothesis. Okay, so in words, what that means is, so what's in this model? Well, this is a reduced model with only the acidity. Okay, so this is asking whether it's plausible that the method, so the categorical variable for method, because we're dropping these two, has any impact on the response. Okay, so this hypothesis answers this question. Is the reduced model with only acidity plausible? Okay, and so of course the alternative is that at least one of these betas is not 0. Okay, so what is the A matrix? Well, in this case, you can set it up very similar to our first case, because we now have 2 constraints. So now we're starting to see the pattern. A is now going to have 2 rows for the 2 constraints. Okay, so the first constraint is beta 2 equals 0, so 0, 0, 1, 0, and then 0, 0, 0, 1. Okay, and so so notice that A times beta is now 0 vector, and this is now 1 by 2 for the 2 constraints, and so that captures this null hypothesis. Okay, I want to do one more. Okay, so let's go over here. So here's another example of a hypothesis that can be written using this general linear combination, and that's this one. So let's look at null hypothesis beta 2 minus beta 3 equals 0. And so the alternative is beta 2 not equal to beta 3. Okay, so again, so if the null hypothesis is true, we get a reduced model. Okay, so what is yi then? So we're saying in this case that null hypothesis beta 2 and beta 3 are the same. So what are they referring to? Well, beta 2 and beta 3 are the effects of the semi treatment versus the wet treatment. And so if they're the same, then we're saying that we're asking whether the effects of these two methods of processing have the same impact on the response. Okay, so that hypothesis has a natural interpretation. Okay, so what does the reduced model look like? Well, you'll have beta 0 plus beta 1 xi1 plus, okay, so they're the same, so I could just call it beta 2 xi2 plus xi3 plus epsilon. So basically what this does is it says these two are the same. So in fact, when you add up these two indicators, so this is equal to 1 if we use either the semi or wet method, and then 0 if we use the dry method. Okay, so now if the null hypothesis is true, we only need one parameter to cover the difference between semi and wet and dry, and this hypothesis says that semi and wet would have the same effect. Okay, so let's write that in words. So interpretation are wet and semi methods are their impact do the wet and semi methods have the same impact on the response. Of course, we have to interpret it holding other variables fixed, so we have to hold acidity constant. Okay, so this is the question answered by this hypothesis test. Okay, and so again, this hypothesis can be written as in that general linear form. So what's the matrix A now? Well, there's only one constraint, and it's beta 2 minus beta 3 equals 0. So if you write beta 2 minus beta 3 equals 0 in this matrix multiplication form, so the coefficients, so for beta 0 is 0, for beta 1 it's 0, for beta 2 it's 1, and then for beta 3 is minus 1. And so once we multiply A by the vector of parameters, then that gives us beta 2 minus beta 3 equals 0. So this hypothesis can also be written in that general linear form. Okay, so looking back at what we've done, we've seen a number of different constraints in the setup of these matrices for A. So let's just label them. So here there were three conditions on the betas. Okay, so we have 3 constraints, and over here we had 2 constraints. and then here we have just a single constraint. And each constraint can be written as a linear combination of the parameters. Okay, so this illustrates the kinds of hypothesis tests that we can do using this general linear form. Okay, so each of them has a matrix specifying the coefficients on the betas, and so specifying the matrix A fully specifies the constraints. So we can write each of these and interpret each of these hypotheses, and then do the actual hypothesis test using this general framework, which, as we're leading up to, will be based on the F distribution. Okay, so I think this example helps illustrates what we can do with this framework of hypothesis testing. Okay, so now let's move back to the general case and get us to how we're going to use and make use of the F distribution and why it is related to these general linear hypothesis tests. Okay, so the first point I want to make is, well, in general, if we have a bunch of constraints, then we now know the dimension of the A matrix in general. So let's write that down first. Okay, so in general, if we have, let's say lowercase l, so if L constraints, so we've learned now that A will be a matrix with that number of rows, and that is also the rank of the matrix. So A is a L by P plus 1, because P plus 1 is the dimension of the beta vector of the parameters, beta 0 and then beta 1 to P. Okay, so it is a matrix with rank L. Okay, so there's no duplication in the specification of the constraints. Okay, so now when we did estimation for multiple linear regression, I gave you a geometric interpretation in terms of span. Okay, so recall. So let's go back to that and let's add to that picture now. Okay, so recall that we could write the matrix, we could write the explanatory variables x in matrix form. Okay, and so the span of its columns that we looked at, so it includes all these possible vectors in n-dimensional space. Okay, so beta 1, so remember each of these x vectors represents that column in our matrix of predictors. Okay, so that was the span we worked with when we were talking about when we drew the picture for the geometric interpretation of our least squares solution. Okay, and so the key here is to now write another span corresponding to this reduced space, this space with the constraints. Okay, so I'm gonna define a new span. Let's call it span. Okay, I'm gonna put a subscript A to indicate that is the span after accounting for these constraints. Okay, so this what's in here? Well, it's the same thing. Beta 0, 1. Okay, so the linear part is the same, but now there's a constraint. It's all these possible vectors. Okay, with these betas as the coefficients multiplied on the vectors of x's with this constraint that now a times beta, this vector, equals 0. Okay, so originally each of these betas could be any real number. Okay, so this is the space, the n-dimensional space spanned by the columns of our matrix X. Okay, and so this is the restricted span to satisfy the condition of our matrix of constraints. Okay, so so the first thing we can note is that, so this restricted span is a subspace of span of X. Is a subspace of span X, and how do we know that? Well, any vector that's in span A is also in here. Okay, since any vector in this restricted one is also in the original span of X by construction. Okay, so in words, what we've made here is we can call this guy the span with the restriction. With the constraints matrix A applied on beta. Okay, so with that in mind, let's draw another picture after this idea. So we're going to start with the picture that I drew for getting our least squares to give the intuition, geometric intuition for least squares estimate. So let's start with that. Okay, so in that picture I had I had this representation for the span of X, and then we had this representing the vector of responses. Okay, so recall that the vector of responses is generally not going to be in this span because the x's generally aren't going to perfectly predict y. Okay, so remember that in our least squares framework, we found the fitted value, so that's here. Okay, so we draw this. Okay, so this is orthogonal. Okay, so down here is the fitted value, so mu hat. Okay, so that's this point. Okay, so remember that mu hat is in the span because mu hat is x times beta hat. Okay, so beta hat is our least squares estimate, so that gives us our fitted values mu hat. And so also recall then that this difference between the observations and the fitted value, so this vector difference is the vector of residuals. Okay, so let's label this. So this difference is E. Okay, and so the key now is we have set up a different span, which is restricted. So let's draw a smaller span. So let's draw it over here. Okay, so let's say this piece represents the span, this restricted span. Okay, so now let's imagine fitting a regression model subject to the constraint. So that's why I wrote in the example the corresponding so-called reduced regression models. So for example, in the second case, if we're dropping the method of coffee bean preparation from the model, then we would be fitting a regression model with only acidity. Okay, so this is what we mean by fitting a reduced model. Okay, so let's define this notation. So that's mu hat A. Okay, so denote the fitted values from fitting the reduced model. Okay, so imagine going through that process. So we use the constraints and simplify our X matrix, and then we fit the model on the reduced set of variables. Okay, and we obtain fitted values. And so by construction, of course, this vector of fitted values from the constraint space is going to lie on within the reduced span of X. So it's going to lie in this green region. Okay, so I'm going to draw that here. So mu hat A is going to be in span A by construction. Okay, so let's put that point here. Okay, so we'll call this mu hat A. Okay, so that's this point. Of course, as we would know, if we're taking the vector responses, and then so you're going to have this. We're going to have this new orthogonal projection. So of course, this within this reduced span, this residual vector is going to be orthogonal to the green part. Okay, and so while we're at it, let's label this segment. So this is now the difference between y and the fitted values on the reduced model. So y minus mu hat A. And so while we're at it, well, this is so what's the interpretation of this quantity? Well, it's the residual. If we fit based on fitting the reduced model. Okay, so let's call this E subscript A. Okay, so let me write that in words. So this thing is the residual. If we fit the model with the constraints A beta was 0. Okay, so this is the picture. Okay, so imagine we're fitting the model twice, once to the full set of predictors, and then one to the reduced one. Okay, so this is what it would look like. So in practice, we would expect there might be some differences, as sort of indicated here in the picture, between these two sets of fitted values. but there's going to be some relationship between them. Okay, so let's talk about that next. So if the null hypothesis is true, so if A times beta is the zero vector is true, then what can we say about these two fitted value vectors? Well, they're going to be close. Okay, so let's see why that is. Okay, so then so the fitted values from the full model and the fitted values from the reduced one, mu hat A, will be close. Should be close. Okay, so why is that the case? Well, when you think about it intuitively, so if indeed there is no significant effects in the part of the model that we threw away, then both the reduced model and the full model should be making similar predictions. Okay, so these 2 points should be close, and so that's the idea that we're getting at. Okay, so what I mean by that is the model should make similar prediction. Similar predictions whether we force this constraint or not. The fitted values should be similar, making similar kinds of predictions. We want to make similar predictions whether we set this constraint to 0 or not. When fitting the model. Okay, so if this is plausible, then we shouldn't need the betas associated with this constraint when fitting the model. They won't contribute. If this is in fact true, then these betas won't contribute much at all to the prediction of y. And so that's the key idea that we want to get out of this picture. And so what we want to do then is assess this vector difference. So let me draw that here. Okay, so imagine connecting these two points in n-dimensional space, mu hat A and mu hat. Okay, so here's the intuition then. So what do we mean by should be close? Okay, so to assess whether this null hypothesis is plausible, what should we do then? Well, we should take the difference, the vector difference between these two vectors of fitted values, and look at whether that is small. Okay, so in other words, close to 0, in which would be consistent with the null hypothesis, or whether it is large. If these are far away, then that means there is additional information in the x's that we omitted in the reduced model. Okay, so to assess whether null hypothesis is plausible, we should look at. Okay, so what specifically what I mean is the magnitude of the vector difference. Okay, so we're taking the difference of these two vectors. So we're taking mu hat A, fitted value, and then for the reduced, and then the fitted values for, I'm going to write this one. I write the fitted values for the full model minus the fitted values for the reduced model. And we're going to look at the magnitude, so I'm going to use this notation, so double bar. And so when I write double bar, I'm talking about in this case, I'm just talking about the Euclidean distance between the two vectors. So this is what it represents, or we can also call it the L2 norm of this vector difference. Okay, so let me just write that out specifically. So I write double bar mu hat minus fitted values from the reduced model. We're talking about the Euclidean or the L2 norm. Okay, so how do we represent distance? So we need to take the square root, right? So and then you can write it as the dot product. So this is just a more compact way of expressing the Euclidean distance, right? If we take the difference of each coordinate square, add them up, and take the square root. So we're written compactly in vector notation. So mu hat minus mu hat A transpose times the vector difference, so that gives us the dot product, and square root of that gives us the Euclidean distance between the fitted values from the full model and that of the reduced one. Okay, and so let's write the intuition. So if this distance is so if it's large, okay, and then how large? Well, this is why we'll need to introduce a probability distribution that governs that governs the quantity that we can use then to do the formal hypothesis test. So we'll need, this is where the F distribution is going to come into play. That will give us the appropriate cutoff for what is considered large. But suffice for now to say, if it's large, then that means it's evidence against the null hypothesis. Okay, so when we look at whether if it's large or small, okay, and small means like, because this is the distance, notice, so it has to be greater than or equal to 0. Okay, so small here means close to 0. Okay, so what we're saying is if this distance is large, then this is evidence against the null hypothesis. And then if it's small, then this is evidence in favor of the null hypothesis. For the null hypothesis. Okay, so that's the intuition. So what we need to do now is look at the relationship between this vector difference and these other quantities we have in this picture. And so what you notice here is that both of these are in the span of X. This mu hat A is in the reduced, the span of the reduced model. Okay, and so what we want to focus on is this triangle here. Okay, so we're going to use probably one of the first theorems we learned in grade school, and so we have a triangle, and this is a right angle. Okay, so that should remind us of the Pythagorean theorem, right? So this is due to Pythagoras. So let's see how that applies here. So we have these three sides, and so we know that a squared plus b squared equals c squared. Okay, and so specifically in the notation that we have, what does it look like? Okay, so let's by Pythagoras. we have the hypotenuse is the vector difference between the responses and the fitted values and the reduced model. Okay, so let's write this in full first. So we have y minus mu hat a. Okay, and then we're looking at this, and the theorem is written in terms of square distances. So we'll put the square here. So that must be equal to this side squared plus this side squared. Okay, so we've written this one as, okay, so let's just write it out in full. So y minus, so the residual in the full model, and this quantity which we just defined, the difference in the fitted values between the full and reduced models. Okay, and so let's substitute some of the things we defined here. So we know that this this one is the residuals. Okay, so in other words, we're saying equivalently that the residuals under the reduced model is equal to the magnitude of residuals in the full model, and then plus this term. Okay, so what is this written as? So this is simply, or equivalently, we can write this as E transpose A, and then this one is E transpose E. Okay? So using the definition. So this is the squared. It's the sum of the squared. So you take each residual, square them, and we sum them up. That's what's represented by this operation. So in fact, we have seen already names for these. So in our last lecture, we did sum of squares decomposition, right? So what is this one? My bad, I don't need a hat on top of the residual, so let me get rid of that first. Okay, y minus mu hat, so that by definition is the residual, so let me get rid of these. Okay, that's better. And I'm missing an A here. Okay, so this is the, yes, so in terms of sum of squares, now we see the connection here. This is simply the sum of squares residual in the full model, and then this is the sum of square residual in the reduced model, expressed as the vector dot product. Okay, so that's the key point here. Okay, so let's label these. This guy is simply the sum of squares residual. Okay, let's call it sum of squares residual under the reduced model with the constraint A. And then this is the sum of squares residual from last time that we already saw. Okay, so this is as previously as defined for the full model. Okay, and so we now have this relationship between the full model and the reduced one. Okay, so thus we can say this difference between fitted values can be expressed as sum of squares residual from the full model minus the sum of squares residual from the reduced one. And so, as we already argued, this is a difference vector, the magnitude of a vector difference. So this is non-negative. So I'm writing to the 0 here. So what is this? What do we call this thing then? This is a difference between two sums of squares. So we'll call it as follows. This is the additional sum of squares explained by the full model. So this is additional sums of squares explained by the full model versus the reduced one with constraints A. Okay, so this has a practical implication because it tells us, gives us this fact about the relationships between the sum of squares residual when you add or take away predictors from the model. So let's briefly talk about practical implications. Okay, so what does that mean then when we fit full models and fit the reduced models? So what can we say on a practical note? Practical implications. Okay, I'm going to say it in two ways. They're basically the same thing. So the first is that, so we're looking at the sum of squares residual. So what happens when we for example, take away predictors from the model? According to this relationship, the sum of squares residual cannot decrease. Okay, so cannot when applying constraints. Okay, so why is that? Why is that important? Well, it says that you cannot fit the model better. Okay, so remember we have the sum of squares residual relative to the sum of squares regression, right? In our ANOVA decomposition. So the model fit cannot improve when we apply constraints or take away predictors from the model. Okay, so or equivalently. We can say it in another way, is that the full model. Okay, so the full model has potentially more predictors than the reduced one. Okay, always has a smaller or equal, so has a okay, so the key is it can't be larger. Has a smaller sum of squares residual. Okay, and why is that important? Well, because recall that the responses y that we're trying to fit hasn't changed. We're only changing what we're using from the matrix of predictors x. Okay, so remember so in other words, y is not changing, so the sum of squares total is not changing. Okay, so for a fixed sum of squares total. Okay, so what does that mean? So that means if sum of squares gets smaller relative to the fixed total, then that means the sum of squares regression is relatively larger. So therefore, what does that mean in terms we defined last time? That r squared will be higher. So the full model will always explain as much or more of the variability in 1. Okay, and thus higher value of r squared. Compared to the reduced model. Okay, and so that has to be true because the sum of squares total is fixed. Okay, and this will have important implications when we talk about, as we discussed later, well, which predictors should I include in the model? Well, I mean, it's good to have all these predictors, but maybe some of them are not impacting the response. And so we fit a model, including certain predictors might not actually help us predict the response. So this tells us that even if you include non-importance predictors, r squared isn't going to go down. Okay, so that's what this says. And so we need a way to assess, well, how much, for example, how much of an increase in r squared, for example, should justify us including certain variables in the model. So we'll come back to this point in practical applications where we have large sets of predictors. Choosing which ones to include is going to be an important question, which is called model selection. Okay, but for now, let's finish this discussion by talking about the F statistic. Okay, so this is based on what we said here. Okay, so it makes sense then that we'll build a test statistic based on this expression, right? So the difference between the sum of squares. Okay, so remember the intuition. When this difference is large, then we would tend to reject the null. But if it is small and close to 0, then we would tend to not reject the null hypothesis. Okay, so that's the intuition that we're going to now formalize. So we're going to define our test statistic. Okay, so this is, I'm going to call it F, okay, because it's like as we're going to see, the distribution associated with this quantity when the null hypothesis is true is the F distribution, which I'll define for you shortly. But first, while we're at it, let's write down the test statistic. Okay, so we're going to take this quantity, so this difference between the sum of squares. So sum of squares, residual from the full model minus the sum of squares, residual from the reduced one. And we're going to divide that by L, the number of constraints, and in the bottom we're going to take something we've already seen in our ANOVA table, which is the mean square residual. Okay, and then this quantity in the denominator, we've actually seen in the ANOVA table from last time, is simply our estimate sigma squared hat. So this is the estimate of the residual variability in the full model. So it's the estimate of sigma squared in the full model. Oh, okay, I see. So I have a typo here. Okay, so when we were moving the sum of squares from the left hand side to right, from the right hand side to left hand side, I messed this up. So mu the difference here, okay, is yeah. So I have the wrong subscript here. That's why this looks funny. Okay, so let me fix this. Okay, so let me rewrite what I had. So we had y minus mu hat a squared equals y minus mu hat square minus plus difference between the fitted values. Okay, so this was the equation. So clearly I made a mistake when I moved the term over. Okay, so this one again is sum of squares residual, and then this one is sum of squares residual in the reduced model. So clearly I made a mistake here. What I mean is the subscript a here. Okay, so I interpreted it correctly. I said the sum of squares is larger for the reduced model, but then I wrote it down incorrectly here. Sum of squares residual for the reduced model minus sum of squares residual for the full model. Okay, so let's fix that. Okay, so that's why this one looked funny when I wrote it again. So let's fix that. So sum of squares residual for the reduced model minus the sum of squares residual for the full model, and that has to be greater than or equal to 0 by our geometric argument. Okay, that looks correct now. And let me just check what I wrote here. Sum of squares residual can't decrease when constraints are applied. Yes, that's correct, because this one has to be larger than or equal to. And so the sum of squares residual for the full model will be smaller. Okay, so that's correct. And higher R squared. Okay, so that's our F statistics. And now we have these two, both the numerator and denominator are related to sums of squares. So this one is on the top. We have the additional sum of squares explained by the full model, and then on the bottom we have what would be the estimate of the residual variance sigma squared coming from the full model. Okay, so with that defined, let us introduce the F distribution and see how the F distribution is related to this quantity when null hypothesis is true. Okay, so let's take a quick detour to introduce the F distribution. Okay, so here's definition. So if we have two random variables, so we have a chi-square with a degrees of freedom, and then the chi-square with b degrees of freedom, and they're independent. We say that the scaled ratio, so we take each chi-square and divide by its corresponding degrees of freedom. This is an F distribution with the corresponding, so it has 2 degrees of freedom. So what the order is numerator comma denominator, so it's F, A, and B. So these correspond to the degrees of freedom in the chi-square in the numerator and denominator, respectively. Okay, so let's keep this part in mind, and then let's look at these quantities. Okay, so here we need some facts. So here, so in this context, we have these facts. And these are when the null hypothesis is true. Okay, so we already learned about the denominator. It is a chi-square, as we explained when we fitted the multiple linear regression model. Okay, so let's write down. Okay, so this is always this one is always true. So sigma squared times degree of freedom residuals. In other words, this is the sum of square residual divided by the true unknown sigma squared has a chi-square with n minus p minus 1 on degrees of freedom. Okay, and so the new quantity we have to introduce relates to the numerator. Okay, and then the other, it turns out that when the null hypothesis is true, so this is where we need this fact. So when the null hypothesis is true, that gives us this distribution for the numerator. Okay, and that's why we can then use the F distribution to do the corresponding hypothesis test. Okay, so this difference between mu hat and mu hat A divided by the true unknown sigma squared. So when the null hypothesis is true, this one is also chi-square distributed, and that's the fact that we will make use of. It is chi-squared. Degrees of freedom is the number of constraints from the matrix A. So it's chi-square with L degrees of freedom. Okay, so with those facts, and finally these two are also independent when the null hypothesis is true. Okay, so how does that relate to this test statistic? So then, okay, so therefore, this F statistic I defined. Okay, so I can write it as follows. So you can get it into. So basically, what I'm doing is I'm going to write this statistic to match the F distribution form. So what I would do then is take this difference, which represents the difference of the sum of squares, the additional sum of squares explained by the full model. So I'm going to create this chi-square, so divide by sigma squared. And then I'm going to divide by times 1 over L, which I have over here. And in the denominator, I'm going to do something similar. So I'm going to use this chi-square. So sigma squared hat n minus p minus 1 sigma squared. Okay, so that's my chi-square. I'm going to divide by its degrees of freedom. Okay, and so now I have this part is u chi-squared L, and then this bottom is v, which is chi-squared n minus p minus 1. Okay, and then use independence, and so this you notice this part completely matches the F statistic. I just divided top and bottom by sigma squared. Okay, so this is the same test statistic, and so this test statistic, when a null hypothesis is true, follows an F distribution. Okay, so this has an F distribution. Degrees of freedom are L and n minus p minus 1 when null hypothesis is true. Okay, and so we now have the ingredients to finish our hypothesis test. So as we said, we want to reject the null hypothesis when the test statistic is large. So this difference is large. Okay, so if we, in terms of the F distribution picture. Okay, so here is an example of an F distribution plot. It's the ratio. It's essentially the ratio of two chi-squares. Okay, so this is the F distribution. We're going to take a critical value, and then we're going to reject the null hypothesis for level alpha when the test statistic is large. Okay, so key difference between this and the t-test we've done here is we're only looking at the right tail. Okay, so remember that we only reject over here because since large values of test statistic F is evidence against the null. Okay, so therefore we can write our conclusion here. So we reject the null hypothesis that this linear transformation of the parameters, so that's null hypothesis, and we reject it if at level alpha, if F is greater than the 1 minus alpha quantile of an F distribution with degrees of freedom L n minus p minus 1. And we can compute the corresponding p-value. So p-value is the probability that we get and corresponding p-value. So now we just need to look at the right tail. So as equal or more extreme, so equal or larger, equal. So the p-value is the probability that an F distribution is greater than this value we calculated, where we're using this F distribution with again degrees of freedom is the number of constraints, and then the number of residual degrees of freedom. Last thing I want to mention is a connection between the F and the T distribution. Okay, so relation to T distribution. Okay, so let's define a T random variable. So let's say Y is a T distribution with A degrees of freedom. Then we know that Y can be represented as a standard normal divided by root of a chi-square with a degrees of freedom. Okay, so here z is a normal 0, 1, and u is a chi-squared a degrees of freedom, and they are independent. Okay, and so then that implies that if I square y, so y squared, so I square everything on the right hand side, we get z squared, and at the bottom you have u over a. And so remember that the square of a standard normal, okay, so this guy, is the square of a standard normal is a chi-square with 1 degree of freedom. Okay, so we put a divide by 1 here, just for emphasis. Okay, so now we have a chi-square 1 divided by 1, and bottom we have a chi-square a divided by a. And so that, by definition, is an f. So the square of a t distribution is an f. And it's an f with one numerator degree of freedom, and a for denominator degree of freedom. So what does this tell us in terms of the connection between the t-test and the f-test? Is that when are we going to have L equals 1? Okay, we're going to have L equals 1 in this general hypothesis testing framework when we're only imposing one constraint. Okay, so what does one constraint remind us of? Well, it reminds us of things we've done for t-tests. So for example, testing beta 1 equals 0, right? That can be written as using an A matrix of just one row. Okay, so what we see there, therefore, is that so if our hypothesis test, so this tells us if has just one constraint. Okay, so for example, null hypothesis beta 1 equals 0 versus beta 1 equals not equal to 0. Then this f-test we just talked about is equivalent. To the t-test of the same hypothesis. Okay, and so that shows then that the f-test is indeed a generalization of the t-test, so that we can handle more combinations of the parameters in terms of what the hypothesis is written as. So in particular, as we saw at the beginning of today, we can write these general linear hypotheses that allow us to, for example, ask whether the entire regression model is significant or not. It allows us to take variables out of the regression model and ask if that set of variables are significant. And that also allows us to look at a difference, whether two categories in a categorical variable, for example, have the same impact on the response. So those are the three kind of motivating cases that I showed you at the beginning of the lecture. Okay, so that's all for today, and then when we come back, we are going to look at how to carry out some of these tests in R, and then so we can see that illustrated with some numerical examples.